Hello everyone, welcome to Graph Theory Day 2. Today we're going to be talking about the shortest path. Alright, so yesterday we talked about the very basics of graphs and networks. We talked about the parts such as the vertices and the edges and things like that. So today we're going to actually talk about one of the most common applications of graph theory, which is just finding a shortest path through a network. Alright, so a network being a system of connected edges and vertices. All right, and this is actually something that is done almost every day, millions of times by things like Google Maps and smartphones and GPSs, and things like that. So when you're trying to find directions, it usually calculates where you are and it looks at where you want to go, and it uses the streets as edges, right, that you're going to travel. And Google knows the length of those streets. It knows about traffic. It knows about all kinds of things as it calculates in how long it would take you to get from point A to point B along several different routes. And it constantly reevaluates those routes to find the shortest route or the quickest route when you search for something on Google Maps. So super applied. This algorithm I'm going to teach you is the basis for the coding in Google Maps that will help you find shortest path from point A to point B. All right. So this algorithm that is used is something called Dijkstra's algorithm. All right, and the steps are listed here. All right, and I'm going to go through those steps with you. I'm not going to read them out to you, but I'm going to go through them and show you how it's done here in this first example. All right, so let's take a look at what we got here. All right, so let's suppose that we are traveling from Tacoma, Washington to Yakima, Washington. All right, Tacoma is represented by vertex T, and Yakima is represented by vertex Y. And these are all of the routes or all of the possible roads that you could take in between. Right? So this is what Google sees when it starts to do this algorithm. All right. Now these numbers that you see assigned to the edges, these are what's called weights. All right. This is the calculated time that it would take to travel from vertex T to vertex A. All right. So it would take 20 minutes. Going from vertex Y to vertex MR here, it would take 96 minutes. All right, so our goal is to get from Tacoma to Yakima in the shortest amount of time possible, and Dijkstra's algorithm will do that for us. It will always find the shortest path, and it's what's called a light load algorithm. In other words, it doesn't take a lot of calculations to do this algorithm, so it's really easy on a computer. Right, so a computer can actually use Dijkstra's algorithm without putting a lot of processing load on the processor and the components of the computer. All right, you probably don't care about that, but this is a really good algorithm for a lot of different reasons. All right, so let's go ahead and start this off, and I'm going to zoom in just to make this graph nice and big for us here. And I'm going to change my pen. And we're going to come over here and we're going to start this algorithm. So the first thing you want to do is you want to go and mark your start and your end point. Remember, we're starting at vertex T, so we'll call this the start, and Y is the end. Okay, and our algorithm actually starts at the end, ironically. All right, so what we're going to do is we're going to take a look at vertex Y here. Since it's the end, we mark it with a 0, and the reason that we do that is because it is 0 away from the end. All right, so if you read step 2, it says find all the vertices that lead into the current vertex. This is going to be our current vertex right now. We're at the end. All right, and we're going to find all the vertices that lead into it. So I can see 3 vertices. Right, if I track these edges back, I see 3 vertices that lead into vertex Y. There's NB, MR, and P. Right, so if I go up here to NB, it wants me to calculate the distance from NB to the end, which is Y, right? So we can see from the weight on the edge here that it is 104 away. So I'm going to mark NB with a 104. All right, and I'm going to put a Y next to it. And you'll see why I do that at the end, okay? So since I went to NB from Y, I put a Y there. Then I go down here to MR and I do the same thing. MR is 96 away, so I'm going to mark it with a 96, and I'm going to put a Y next to it. And then you do the same thing for P, right? Because P leads into Y, and P is 76 away. And I'm going to mark that one with a Y too. All right. Now, once I've analyzed all of the vertices that lead into my current vertex, I mark that vertex as visited, or just mark it so that we don't analyze it again. All right. So you might put an X through it, you might circle it, whatever. I like to circle particularly because I want to be able to see the label for that vertex, so I like to circle the ones that I have visited. So now I know I'm not going to analyze any edges going back into Y. All right. Now, step 4 says mark the vertex with the smallest distance as current and repeat step 2. All right, so I'm going to go to these vertices that I have analyzed here, and I'm looking for the shortest one. Right now, the shortest one is 76. It's 76 away from the end. So this is going to be my current vertex. This is where I'm at right now. And I'm going to analyze all the vertices that lead into P. Right? So I have 2 of them. I have E and I have MR. Okay? So let's do E first. All right, so E, right, we want to calculate its distance from the end. Well, its distance from the end would be 96 plus the 76 that it took to get to P. So I do 96 plus 76, which gets me a total time of 172. And I'm going to mark that with a P since I came through P. All right. Then I do the same thing for the other vertex that leads in, so that's going to be MR. All right, so if I do 76 plus 27 to get to MR, well, that would give me a grand total of 103, and 103 is bigger than the current distance that I have at MR, so I'm not going to write that one down. Now I've analyzed all the edges that come into P, so P has been visited. I circle it, that way I don't revisit it again. And then I repeat the process again. So now I'm looking at E, I'm looking at MR, I'm looking at NB, and the shortest distance here is the 96. All right, so I'm going to make this my current vertex, and there's only one edge that I need to analyze because the other 2 edges lead back to visited cities. So I don't need to analyze the 27 again. I don't need to analyze the 96, but I do need to analyze the 79. Okay, so if I do MR to A, I'm going to do 96 plus 79, and I'll get a distance here, right? 96 plus 79 is 175. And I'll mark that with an MR, right? Because I came from MR. Like I said, the vertices that I'm putting next to these numbers, you'll see why I do that at the very end. All right. Now MR has been visited, so I'm going to circle it. And I look at all of my vertices again, right? I have a 104, I have a 175, and I have a 172. So I'm going to go back to NB, that's my smallest vertice right now, and I'm going to analyze all of the edges that lead into NB. This one leads back to a vertex we've already visited, so I don't need to do that one. But this one I need to do. I haven't made A my current yet, so I can do 104 plus 36, and that's a distance of 140. So I'm going to write that one down because it is currently a shorter distance than 175. So to get to A, it would be shorter to go through NB to A rather than going through MR to A. Okay, so I'm going to put an NB next to this one, and I'm going to cross out MR. All right, and now NB is done. So again, I reanalyze my vertices. So I have this one up here, vertex A with 140, and this one down here, vertex E with 172. So the 140 is shorter, so I'm going to go up here to vertex A. I have 3 edges. 2 of them lead back to visited cities, so we're done with those. So I just need to analyze this one, which takes us back to our start point. So if I do 140 plus 20, it gets me a distance of 160. And I'll mark that with an A. Okay. So now A has been visited, and there's only one left. And if I come down here to vertex E, I notice the distance to get to E is already 172, which is longer than the distance that I have to the place where I'm going, which is 160. So I'm done with this. I don't even need to analyze it because I already know that whatever numbers I add together here are going to be bigger than the 160, so I don't even want it. All right, so we have completed the algorithm. Now let me show you how to get your path. Okay, so remember this is our start point. We're starting at T, so I'm going to say T2, and you'll notice it tells you where to go, A. So I'm going to say T to A. Then once I go to A, it tells me where to go next, NB. All right, and then once I go to NB, it tells me where to go next. It tells me to go to Y. And the other really cool thing about this algorithm is it has already calculated the length for me here at 160. Right? So this is my shortest path from T to Y, and this is the length of that path. Right? So as we run that algorithm, we are doing all of the simultaneous calculations that we need to make sure that we are testing every possible route and finding the shortest one. So it finds the route and automatically calculates our shortest path. Right? Really cool algorithm. This is used so much you have no idea. All right, and there's a quick blurb down here, just more information on Dijkstra's algorithm being optimal, which means it always finds the shortest path. It's not going to provide something that's kind of short. It's going to provide the shortest path every single time. And it's also efficient. It doesn't require a lot of calculations, which makes it nice and easy for computers to handle. All right, let's try it one more time. Make sure we got it nailed down. I know you're probably thinking like, wow, that seemed really hard, but once you practice it and get going with it, it's not that hard. All right, if you can add, you can do Dijkstra's algorithm. All right, so it says find the shortest path from A to L. No problem. All right, so here's A, and A is our start, and L is our end. All right, so remember, start by marking your start and end point, and then also remember that Dijkstra starts at the end point. Right, so L is our end, so I'm going to put a 0. And this is where my 0 is. I am 0 away from the end. Now I analyze all of the edges that come into L. So I've got 2 edges that come in, 13 and 23. So we'll go over here to I first. So we're going to say that I is 13 away, and I'll put an L there. Right. So this is like leaving my breadcrumbs, right? If you notice what I did with these in the last example, I use these to trace my path back through the mess, okay? So these are like breadcrumbs that I'm leaving behind so I know how to get back to the end, all right? So I do the same thing down here with K. K is 23 away, and now I have looked at every edge that goes into L, so L is visited. So I'm going to circle it, that way I know not to go back to it. I look at my 2 vertices that I've looked at. The shorter one becomes my current, right? So now I'm at I, and I have 2 edges that go into I, this 1 and the 24. So I'm going to go to F first. So we do 13 plus 1. So F is 14 away from the end, and I'm going to put an I next to that one. We do the same thing down here, right? 13 plus 24. So H is 37 away from the end through I, and now I is done. So I circle it. I don't want to go back to it. All right, I analyze my current vertices. I have a 23, a 37, and a 14, so I'm going to go with the 14. All right, I have 2 edges coming in, so 14 plus 4 gives me 18 through F. And then 14 plus 21 gives me a 35 through F. F's visited. Okay. Again, I analyze my vertices, right? So 18, 36, 37, 23. 18 is the shortest. So I'm going to analyze all the vertices or the edges coming into vertex C. So I have 2 of them here. One goes back to a city that's been visited, so I don't need to do that one. This one does not, so I'm going to do 18 plus 3, which gets me a distance of 21 to vertex B through C. Okay. Now I'm done with C. Okay, so again, I analyze. Right, 23, 37, 35, 21. 21 is the shortest again. So I'm going to analyze these 2 routes here. All right, so if I do 21 plus 20, that's 41. Well, E currently has a distance to it of 35, so that's shorter. So I'm not going to replace it. All right, then I come down here and I got to do B to A, so I do 21 plus 8, which gets me a 29. And that is through B, and now B is visited. Now you might think, well, I'm done. I just found a path to A, but we're not sure that this is the shortest path yet, right? Because if I analyze my vertices, I have a 23, a 37, a 35, and a 29. So this 23 is still shorter than the 29. It's possible I could find a route from this 23 that ends up shorter than the 29. The only way to know for sure is to go back and repeat the algorithm again from the 23. Okay, so I go to the 23, I have two edges. Okay, if I do 23 plus 14, well, that's 37. I already have a 37, so I'm not going to replace it. 23 plus 5 gives me a 28. Okay, and that's coming through K, and now K is visited. So again, I analyze my vertices. I have a 28, a 37, a 35, and a 29. 28 is still shorter, so we're going to do it one more time here. And I only have one edge that I need to do because the other one leads back to K. So we're going to do 28 plus 27, which is a distance of 56 through J. Now J is analyzed, and now when I look at my remaining vertices here, I have 56, 37, and 35. All of those are longer than the 29 that I currently have. So at this point, it is safe to stop the algorithm. There's no point in continuing it anymore because any other route that I find here is going to be longer than the 29. All right, so now I need to write my answer. Okay, and I'm going to write it in a format that's MyOpenMath friendly here. All right, so we're starting at A, and it tells us to go to B. Once we're at B, it tells us to go to C. So I go to C, cut that off a little bit there. So when I go to C, it tells me to go back to F. Once I'm at F, it tells me to go back to I. Once I'm at I, it tells me to go back to L. And L is the end, right? We wanted to go from A to L. So there's my shortest path, and its distance is 29. Okay. So that is it. And this is how, if you're on MyOpenMath doing this problem, this is how you want to enter it in. A sequence of letters, no spaces, no dashes in between them, just A, B, C, F, I, L, all capital letters. All right, otherwise MyOpenMath marks it wrong. I can't figure out why it won't let lowercase letters in there, but it wants uppercase letters. All right, so make sure you capitalize, and if it asks for the distance, make sure you give the distance. All right, guys, that's it for today. We'll practice this some more tomorrow. Have a great day.